Hey guys, welcome back to my CCNA 200-301 course. This is the second part of Spanning Tree Protocol Concepts. Are you ready? Let's get started. One of the CCNA topics you need to learn about STP is STP port states and roles. Let's begin with the states. For each state, you need to know three things: whether it is a transitory or a stable state. Second, whether the switch port will learn MAC addresses in that state. And finally, whether the port will forward data frames in that state. Starting with STP port states. First, blocking. Blocking is the initial state of each port when the switch powers on. It is a stable state where the switch will neither learn MAC addresses nor forward frames. If there is a connection on the port, STP will transition the port from blocking to forwarding, but it must first pass through several transitory states, or basically a couple of them. The first transitory state is called listening. In this state, the switch clears unused MAC addresses from CAM table. The switch will not learn MAC addresses or forward frames in this state. Next transitory state is called learning. In this transitory state, the switch begins to learn MAC addresses on the port, but does not forward frames yet. If everything proceeds correctly and placing the port in the forwarding state does not create a loop, the port will enter the stable forwarding state, where it can learn MAC addresses and forward frames. The final stable state, where the port neither learns MAC addresses nor forward frames, is called disabled. This state is not part of the STP operation and occurs when you, as the administrator, shut down the port. To summarize, the only state in which the port forwards the frames is forwarding. The port learns MAC addresses in two states: forwarding and learning. For RSTP, we have similar states with a couple of differences. First, in RSTP, both blocking and disabled are called discarding. Second, the listening state has been removed from RSTP, so we don't have listening state in RSTP. Please remember that RSTP states do not operate with the STP timers, which we will discuss them shortly. For STP, there are 4 port roles. First, root port. This is the port on a non-root switch that is chosen to reach the root bridge, and it is always in forwarding state. Next is the designated port. Basically, designated ports are the ports that are moving away from the root bridge, like the root bridge interfaces themselves, or the interfaces on non-root bridges that are connected to the endpoints, or when you have a redundant path, the interface on the switch that has a lower bridge ID. Anyway, in the designated port role, port will be still in the forwarding state. Third one is blocked port. This port is neither a designated port nor a root port. These ports do not forward traffic, but listen to and process BPDUs. And finally, disabled port. Similar to its port state counterpart, this occurs when an administrator disables the port or shut down the port. And in this state, the port cannot forward the traffic or listen to any type of traffic. RSTP port roles are similar to those in STP, with a couple of new roles introduced. The root port and designated port roles remain the same. The new rows are alternate and backup ports, which function similarly to the blocked role but behave differently. The alternate port provides an alternate path to the root bridge. If the current root port fails, the switch can quickly designate the alternate port as the new root port, significantly reducing RSTP convergence time compared to STP. I'll be talking about the convergence process in a second. Backup port, which is also known as backup designated port. This role is seen when a hub is present in the network and the switch detects its own designated port BPDUs on another port. And then the switch blocks this redundant path and designates the port as a backup or backup designated port. Lastly, the disabled port role in RSTP is the same as STP, where the interface is manually shut down by the administrator. Now let's delve into the STP timers. As previously mentioned, once the network topology is established and all devices comprehend their roles and states, the root bridge initiates a transmission of hello BPDUs every 2 seconds, disseminating these messages across the network. While this default 2 seconds interval can be altered, it is generally advised to maintain it. The subsequent timer, known as a max age, signifies the duration the switch will remain idle before reacting if it stops receiving BPDUs on the current root port. In STP, this duration is set to 10 times the interval of hello messages. Therefore, by default, it is 20 seconds. However, RSTP has trimmed this to 3 times. So for RSTP, it's 6 seconds. Forward delay denotes the period during which a switch remains in listening and learning states as part of the transitional process. The default value for forward delay is 15 seconds. Cisco Packet Tracer is one of my favorite simulators. Nowadays, if you want to use it, you just need to register an account with Cisco Network Academy and you'll be able to use this product. And my favorite part of this product is this simulation. At the moment, I actually just filtered the STP traffic. So it shows me only the STP packets on the network. But as soon as you click on this play button, it shows you how traffic actually flows in your network. And I want to show you the first thing, which is STP hello messages. Every 2 seconds, as you can see, my root bridge sends the STP messages to the all connected interfaces, and those devices relay the same messages to the all other connected interfaces. And as you can see, when the packets receive at the switch, they get a green tick. But when they go to the PCs, they have a red cross on them, which means that if that STP packet goes to the switch will process that one, but the PC will not process it because the PC is not a switch and it doesn't understand the spanning tree protocol. But switch has to send all of these interfaces, all of these packets, to all connected interfaces to understand who is connected to the network and also be prepared to prevent any potential loops in the network. Now let's talk about the convergence time. Convergence time means if a topology change happens in the network, how long it's gonna take for my network to be converged. I mean, go back to a stable situation. At the moment, this switch is my root bridge. I want to know if this link fails, how long it's gonna take for my switch 0 to enable this port again and use it as a root port to reach to the root bridge. In STP, as I mentioned before, by default, it takes 20 seconds for the switch to react to this situation based on the max age timer. And then this interface first goes to listening state, and then it goes to learning state, and each of these states actually takes 15 seconds. So 30 seconds in total, and hence it will take 50 seconds for spanning tree protocol 802.1d to actually be converged. Now let's see this convergence in action. On this PC, which is PC1, I'm pinging the other PC. So 192.168.1.1, which is the other PC. And as you can see, it is pingable at the moment. But if I go to this switch and delete, not that one actually, this link, my connection actually get disconnected. And if I go to this switch now, you can see the event. And if I run show spanning tree, which I will be talking about the commands in the upcoming video, you can see that this other interface, gig02, is changed to listening state. And after 15 seconds, it will go to learning state. And finally, when the switch makes sure that it doesn't create any loop, it will take the interface into forwarding state, and actually role changes to root port. And now my network is converged. So you can see that my pings are back. This is actually the advantage of having redundant path in the network, but STP in compared to RSTP is not very fast to converge. I changed the spanning tree mode on these three switches from STP to RSTP. I'll show you in the next video how you can do that. And now we want to test our convergence time in rapid spanning tree protocol situation. So I run my command once again to test the connectivity between PC1 and PC0, and have a look at this switch first. If you run show spanning tree here, first of all, you can see that the spanning tree protocol is RSTP now, and my redundant link is actually, the role is alternate at the moment, and the state is blocking. But the thing is, it is an alternate port, so my switch knows that if the root port failed for whatever reason, it can replace it by this one. Let's see how fast this is happening. So if I delete this link now, not the switch, but the link, you can see that this interface goes to green, which means the acting or forwarding state, straight away. And you don't even see one timeout in your pings. Although Cisco says that the timer, I mean the max age timer is 3 times by default, so it has to wait for 6 seconds, but in the backend RSTP procedure is a bit different to STP in terms of convergence, and it's based on the proposal agreement handshake, which is out of CCNA scope. But you saw that rapid prefix in action, and how faster than STP RSTP can converge your network. Alright guys, this was our today's video. In the next video, I'll show you how you can configure and troubleshoot a spanning tree protocol. I wish you enjoyed today's video, and see you in the next ones.